let us understand the concept of continuous compounding. Generally, we assume that interest is received at discrete points in time, such as at the end of the year, or semi annually, or quarterly, and so on. However, most financial institutions today offer continuous compounding. What this means is that the savings account or fixed deposit earn interest compounded continuously, such as every hour or every minute or even more granular than that. Now, we already know that the more often the compounding takes place, the greater will be the interest accrued. So, in other words, if you are compounding on a quarterly basis, the interest accrued over the year will be more than if you were compounding semi annually. And the same way, if you are compounding monthly, the interest accrued will be more than if you were compounding quarterly. So, if you are compounding continuously, your interest accrued is definitely more than whether you are compounding quarterly or semi annually or annually. Now, the formula that we have been using for compound interest is A is equal to P multiplied by 1 plus R by 100 to the power n. Now, here n is representing the number of compounding periods and R is the rate of interest per compounding period. So if you had a case where the tenure is 1 year and the interest is being compounded quarterly, then n is equal to 4, because there are 4 compounding periods in the entire tenure. And if the annual rate of interest was, say, 10%, then R is the rate of interest per compounding period. So R, which was the rate of interest for each quarter, will be 10 divided by 4, because there are 4 quarters. So R was equal to 2.5%. 10 divided by 4. So here what we were doing is we were dividing this data available for a year, that is time was 1 year, and divided it by 4. Similarly, rate was 10% and we divided by 4. So this factor, which is related to the number of compounding periods, let's introduce that as K. And let's express time in terms of number of years. So the time, which is this, becomes N1, and rate, instead of expressing per compounding period, let's express that as per year. So let's use R1. So let's take N1 as number of years. Let's say R1 is rate of interest per year, and K is the number of times interest is being compounded per year. So now with this relationship, let's express small n in terms of the big N1. So we get n is equal to n1 multiplied by k. Now let's understand this. Now let's take another quick example. Let's say the tenure was 2 years and interest is being compounded quarterly. So in this case, capital N1 is the number of years, which is 2, and k is the number of times interest is being compounded per year. So k is equal to 4 because we are compounding quarterly. So 4 times a year. So our n becomes 2 multiplied by 4, which is 8. Now for the rate of interest, R is equal to R1 divided by K. So with the same example, the total tenure is 2 years, interest is being compounded quarterly, and rate of interest per annum is 10%. So in this case, R1, which is rate of interest per year, is equal to 10. K, which is equal to the number of times interest is being compounded per year, is 4. And so R is equal to 10 divided by 4, which is equal to 2.5. So with using N1, R1 and K, the formula for compound interest amount becomes P multiplied by 1 plus, so R will be replaced by R1 divided by K. So R1 divided by 100 multiplied by K, and to the power of small n becomes N1 multiplied by K. So this becomes N1 multiplied by K. Now if the interest is being compounded semi-annually, then there are 2 compounding periods in an year. So K becomes 2. If quarterly, then K becomes 4. And if the interest is being compounded continuously, then K becomes larger and larger and tends to approach infinity. So in case of continuous compounding, we can express this expression as A is equal to limit where x is tending to infinity, P multiplied by 1 plus R1 by 100k to the power n1k. So for continuous compounding, we have the expression A is equal to limit x tending to infinity, P multiplied by 1 plus R1 divided by 100k to the power of n1k. Now we know that limit x tending to infinity 1 plus x to the power 1 by x can be expressed as E, where E is Euler's constant, that is a number which was found to be equal to 2.71828. So this expression we have to somehow express in terms of limit x tends to infinity into bracket 1 plus x to the power 1 by x. So let's try to do that. So this is equal to, we can take p out and limit x tends to infinity. Now if we consider R1 divided by 100k as x, then we have to express n1k in terms of 1 by x. So let's try doing that. So 1 plus R1 divided by 100 times k. Now to the power of, we have to do inverse of x. So it becomes 100k which is the denominator, now it becomes numerator, divide by R1. Now since we have added this to the power, we multiply by its inverse again to nullify the effect. So multiplied by R1 divided by 100k, and then multiplied by what originally was there, which was N1k. So now because we multiplied 100k divided by R1 with R1 divided by 100k, so this becomes 1 and this remains as it is. So N1k remains as it is. So the expression again becomes 1 plus R1 divided by 100k to the power N1k. Now this expression can also be written as P limit x tends to infinity 1 plus R1 divided by 100k to the power 100k divided by R1 and whole to the power of the remaining, which is R1 divided by 100k multiplied by N1k. Now here we can cancel this k with this k. So our expression becomes P limit x tends to infinity 1 plus R1 by 100k to the power of 100k divided by R1 and whole to the power of R1 N1 divided by 100. Now if we compare this expression with limit x tends to infinity 1 plus x to the power 1 by x is equal to e, so this part here can be expressed in these terms. So 1 plus, and if we consider x is equal to R1 divided by 100k. So 1 by x is equal to 100k divided by R1. So this whole expression is also the same as E. So now our formula becomes P, and replacing this whole thing which is in this red box with E and to the power of N1 R1 divided by 100. So A, which is the amount, is equal to P multiplied by E to the power of N1 R1 by 100. So this is the formula for finding the amount in case of continuous compounding.